Proxima b has been called humanity's best chance for a second home, but that belief may be dangerously wrong. The greatest barrier may not be reaching this distant world, but surviving what awaits after we arrive. Today, we'll reveal whether humans could truly build a civilization there or become permanently trapped beyond any hope of rescue. The final verdict could overturn everything we believe about humanity's future among the stars. Let's begin. The landing is over. After a journey across more than 4 light years, the ship is finally still. Dust moves past the cameras. Somewhere beyond the hull, the nearest known planet outside our solar system waits in silence. But no one opens the door. For the crew, landing was only the first test. The next 7 minutes may decide whether anyone aboard will ever touch the ground. Inside the control room, 4 numbers begin to appear. Outside pressure, surface temperature, radiation intensity, atmospheric composition. Each reading carries the same question: can a human body survive even a brief exposure? That is the first fact every mission to Proxima b would have to confront. Humanity knows that the planet exists. It does not know what standing there would be like. Proxima b is about 4.24 light years from Earth, nearly 40 trillion kilometers away. In astronomical terms, it is next door. Yet, even light, the fastest thing known, needs more than 4 years to cross that distance. A message sent after landing would reach Earth long after the emergency was over. The pressure sensor reports first. If the atmosphere is too thin, liquid water may boil or freeze at temperatures that would seem ordinary on Earth. If it is extremely dense, the pressure could crush equipment not built for it. If the air contains corrosive gases, opening an intake valve could damage filters before anyone recognizes the danger. Then comes temperature. One instrument may face the red star. Another may point toward darkness. On the world that could keep one side turned toward its star, those readings might disagree violently. A comfortable patch beneath the landing gear would not prove that conditions remain safe 100 meters away. Next comes radiation. Proxima Centauri is not a quiet sun. It is an active red dwarf capable of releasing bursts of radiation. The surface reading taken during one calm minute cannot guarantee the next minute will be calm. The hull may be the only dependable shelter, and every minute spent testing the outside environment consumes electricity, cooling capacity, and breathable air inside. 3 clocks are now running. The first measures radiation beyond the hull. The second measures the ship's remaining air. The third measures available power. None cares how far the crew has traveled. None slows down because there is no rescue. This is where the familiar image of Proxima b begins to collapse. It is often described as an Earth-sized world in the habitable zone of the closest star to the Sun. Every part of that sentence sounds encouraging, but each part hides a limit. Scientists have measured a minimum mass of about 1.055 times the mass of Earth. They have measured an orbit lasting roughly 11.2 Earth days. Those are discoveries. They tell astronomers how strongly the unseen planet pulls on its star, and how often that pattern repeats. They do not reveal the ground. The planet's true radius has not been directly measured. Its surface gravity is therefore uncertain. A world with nearly Earth's mass could be denser and smaller, producing stronger gravity, or less dense and larger, producing weaker gravity. The crew cannot infer how heavy their bodies will feel from mass alone. Even the existence of a substantial atmosphere remains unconfirmed. Choosing Proxima b as a home from its mass alone would be like buying a house because someone told you how much the building weighs. The number says nothing about the roof, the doors, the wiring, or the foundation. It confirms that something substantial is there. It does not confirm that anyone can live inside. Back aboard the ship, the atmospheric analyzer finishes its first cycle. Suppose it detects carbon dioxide. That would not make the air breathable, but it could mean the planet can transport heat. Suppose it detects oxygen. That would still demand caution. Oxygen can be produced without biology under some planetary conditions, and a useful percentage means little without safe pressure and without knowing what else is mixed with it. Suppose the instrument detects almost nothing. Then the crew has landed on a world where every breath, every cup of water, and every stable room must remain sealed behind engineered walls. A damaged glove would not be an inconvenience. A failed door seal could become a death sentence. Now, suppose the atmosphere is thick. A dense atmosphere can move heat from one hemisphere to the other, but it can also trap energy. The same blanket that prevents the dark side from freezing could make the bright side dangerously hot. Without direct measurements, both outcomes remain physically possible. The crew has not crossed the distance to discover a simple paradise or a simple wasteland. They have arrived at a question with several scientifically valid answers. Proxima b could be an exposed rock. It could possess a moderate atmosphere that redistributes heat. It could hide beneath dense gases and severe pressure. The available evidence has not selected one of these worlds for them. On Earth, an arriving traveler can step outside, smell the air, feel the wind, and look for water. On Proxima b, those ordinary acts must come after chemical analysis, pressure testing, radiation monitoring, and repeated checks against instrument failure. Human senses are not the first line of discovery. They are fragile cargo protected from it. A green light finally appears above the inner hatch. The crew seals one section of the ship, enters a pressure lock, and waits as machines examine the world again. Outside, the planet remains unseen by every person on Earth. No telescope has yet produced a direct photograph showing its surface. Everything beyond that door is being reconstructed from faint movements, models, and assumptions. The nearest possible destination is therefore also one of the greatest unknowns. And before anyone can understand how dangerous its surface may be, one unsettling fact must be faced. Humanity discovered this planet without ever seeing it. Proxima Centauri looks alone. Through a telescope, no small world can be seen circling it. There is no pale disk, no coastline, no cloud. The star appears as a point of red light, while Proxima b disappears inside its glare. Yet the planet leaves a fingerprint. It pulls. Every planet and star orbit a shared center of mass. Because a star is far heavier, its movement is usually tiny. Proxima b does not drag its star across the sky in a wide circle. It makes Proxima Centauri move gently toward Earth, then away again in a pattern that repeats. Astronomers detected that motion through radial velocity. They separated the star's light into a spectrum, revealing dark lines created when atoms absorb particular wavelengths. Those lines act like marks printed on a ruler. When the star moves toward Earth, the marks shift slightly toward shorter, bluer wavelengths. When it moves away, they shift toward longer, redder wavelengths. The color does not visibly change. The displacement is far too small for human eyes. Sensitive instruments measure it. Imagine a closed door with someone pulling the handle from the other side. The person remains hidden. But if the handle moves back and forth at a regular pace, something must be applying force. Astronomers could not see Proxima b. They saw its stellar handle move, and the movement was astonishingly slow. The planet produces a radial velocity signal of roughly 1.4 meters per second. That is about 5 kilometers per hour, slower than many people jog. From more than 4 light years away, instruments had to distinguish that walking speed motion from everything else happening on a violent star. This was not a single observation followed by an announcement. The signal had to return repeatedly while stellar activity and instrument noise produced changes. The repeating period was about 11.2 Earth days. That rhythm revealed the orbit. Proxima b circles its star at about 0.04848 astronomical units. 1 astronomical unit is the average distance between Earth and the Sun. Converted into a more familiar scale, the planet is roughly 7.25 million kilometers from Proxima Centauri. Earth is nearly 20 times farther from the Sun. That sounds fatal. Place Earth 20 times closer to the Sun and its oceans would suffer. But Proxima Centauri is smaller, cooler, and much less luminous. Proxima b can orbit nearby while receiving radiation that could permit liquid water in some models. The orbit creates a strange calendar. A year lasts only 11.2 Earth days. A 50-year-old person on Earth has lived through more than 1,600 Proxima b years. Birthdays and age would lose their familiar meaning. But the radial velocity signal cannot describe the surface. It provides a minimum mass of about 1.055 Earth masses. The word minimum matters because the method measures motion along Earth's line of sight. If the orbit is tilted, part of the star's true motion occurs sideways, where the measurement does not fully capture it. Think of watching a car on a distant road. A car driving directly toward you reveals most of its speed through its approach. A car crossing diagonally may move quickly while showing only a smaller approach speed. Without knowing the viewing angle, the true motion remains uncertain. The same geometry affects the inferred planetary mass. If the orbit is viewed edge-on, its mass remains near the measured minimum. If it is more face-on, the planet could be heavier. Available evidence favors a planet, but radial velocity cannot settle the mass alone. Normally, another method could answer more questions. When a planet passes in front of its star, astronomers observe a transit. The tiny drop in starlight reveals the planet's size. Repeated transits establish its period. During passage, some starlight can filter through the atmosphere, allowing molecules to leave spectral clues. Proxima b does not transit from Earth's viewpoint. Its orbit never carries it across the visible face of the star, as seen from here. That removes the usual route to a measured radius and transmission spectrum. The value of about 1.02 Earth radii, sometimes listed for the planet, is an estimate based on models, not a direct measurement of its silhouette. That distinction changes nearly everything. Mass and radius together reveal density, helping scientists judge whether a world is dominated by rock, iron, water, or gas. Radius also affects surface gravity. Without a measurement, the planet's interior and conditions underfoot remain uncertain. Two worlds can pull on their stars with similar strength and still be nothing alike underfoot. One may have a large iron core and a thin mantle. Another may contain more water or lighter material. One may hold volcanic gases. Another may have lost nearly every volatile molecule early in its history. The stellar wobble cannot choose between them. The signal demands care because Proxima Centauri is active. Star spots can distort spectral lines. Magnetic regions can imitate velocity changes, and flares inject noise. Researchers compare instruments, examine activity indicators, and test whether the 11-day pattern behaves like an orbit. The evidence for Proxima b is strong. The picture of Proxima b is not. That is the uncomfortable divide. Astronomers can calculate the planet's year precisely. They can estimate how hard it pulls on its star and accurately place its orbit millions of kilometers away. But they cannot point to a photograph and identify an ocean, a continent, or even a cloud. Humanity discovered a destination by measuring a star moving at about walking speed. From that movement came a planet, a minimum mass, and an 11-day year. What did not emerge was a surface. And if the world circles so close to its star, its next secret is not simply how fast it completes an orbit. It is whether the same side has been facing that red light for billions of years. The red sun does not rise. It hangs above the same horizon, hour after hour, year after year. Shadows lean in one direction and never sweep across the ground. There is no morning to wake the settlement. No sunset tells the crew that another day has ended. This may be the natural rhythm of Proxima b. The planet races around its star once every 11.2 Earth days. But moving around a star is not the same as turning beneath it. Because Proxima b orbits so close to Proxima Centauri, gravity may have altered its rotation long ago. The likely result is tidal locking. Earth's moon offers the familiar example. The moon rotates once during each orbit around Earth. Those two motions remain synchronized, so nearly the same lunar face always points toward us. It simply stays turned away from Earth. On Proxima b, the same basic process could keep one hemisphere facing the star while the opposite hemisphere faces space. This does not happen because the planet stops rotating. It rotates exactly once for every orbit it completes. To a person standing on the surface, however, Proxima Centauri would appear almost fixed in the sky. Gravity creates this condition slowly. If a young planet rotates faster than it travels around its star, the star's gravity raises slight bulges in the planet's rock, ocean, or both. Friction prevents those bulges from pointing perfectly toward the star. The star then pulls on the misaligned bulges, producing a torque that changes the planet's spin. Imagine twisting a heavy office chair while someone repeatedly pulls one side back toward the same wall. Each pull removes a little of the unwanted motion. For a close planet, this braking can be powerful. Proxima b lies only about 7.25 million kilometers from its star. Many models therefore favor synchronized rotation. But scientists have not measured the planet's spin directly. Tidal locking is a strong possibility, not an observed fact. Other states remain possible. If the orbit is not perfectly circular, or if the planet's internal structure produces different tidal responses, Proxima b might occupy a spin-orbit resonance. Mercury provides an example in our own solar system. It rotates 3 times during every 2 trips around the Sun. Proxima b could, under suitable conditions, rotate in a pattern that allows slow changes in illumination. That uncertainty matters. A permanently fixed sun would create a climate unlike any inhabited place on Earth. At the point directly beneath the star, known as the substellar point, the red light would remain overhead. Travel away from that location and the star would appear lower, near the boundary between the illuminated and dark hemispheres. It would sit close to the horizon, cross that boundary, and the sky would never receive direct starlight. The first assumption is almost automatic. The bright side must burn while the dark side freezes. That outcome is possible, but it is not guaranteed. An atmosphere can move energy. Air heated on the day side expands and rises. Cooler air moves in beneath it. High above the surface, winds can carry heat toward the night side, where the air cools, sinks, and begins flowing back. An ocean, if one exists, could transport still more energy through currents. The process resembles heating a house with several rooms. If every door is closed and no air circulates, the room containing the heater grows hot while distant rooms remain cold. Open the doors and run fans, and the temperature difference shrinks. On Proxima b, the atmosphere and ocean would serve as the doors and fans, but their existence, depth, and composition remain unknown. With little or no atmosphere, surface temperatures could divide sharply. The illuminated rock would absorb continuous energy. The dark hemisphere would radiate heat into space without receiving direct light. Volatile gases might freeze onto the night side, thinning the atmosphere further in a process known as atmospheric collapse. With the substantial atmosphere, the contrast could be smaller. Winds might prevent gases from freezing out. Clouds could form near the substellar region, reflecting some incoming radiation. The night side might remain cold without becoming a frozen trap. This is why tidal locking alone cannot declare the planet habitable or dead. The spin state sets the stage. The atmosphere, ocean, clouds, and surface decide how the scene develops. For human beings, even a moderate climate would feel unnatural. The body expects light to change. On Earth, a roughly 24-hour cycle helps regulate sleep, hormone release, body temperature, alertness, and digestion. On a world without sunrise or sunset, that signal disappears. Settlers would need to manufacture time. Living quarters could brighten gradually to imitate dawn, remain illuminated through an artificial day, then dim toward a scheduled night. Work shifts would follow clocks rather than the sky. Windows might require shutters, not to block darkness, but to stop an unmoving red sun from disrupting sleep. Energy systems would face an equally unusual map. Solar panels on the bright side could receive nearly continuous light, avoiding the nightly shutdown familiar on Earth. But panels fixed in one location would always meet the star at the same angle. Dust, clouds, flare damage, or equipment failure could interrupt a source that had no natural reset. The dark side would receive no direct stellar power. Cables, storage systems, or other generators would have to support it. The settlement might place solar fields nearer the permanent light and critical shelters farther away, then connect them across terrain where temperature and weather could change sharply. Even the word year would lose its old meaning. 11.2. Earth days would mark another completed orbit, yet no familiar season or sunrise would announce it. A person could celebrate dozens of local birthdays before one Earth year passed. Above them, Proxima Centauri might remain perfectly still for centuries. Then, without warning, that quiet red point could release enough energy to change the sky, the atmosphere, and the settlement within seconds. The first alarm lasts only 3 seconds inside the sealed landing craft. Before the crew can identify it, the radiation monitor settles. The lights remain on. The air pumps continue turning. Nothing outside the hull appears different. 6 minutes later, another alarm begins. Then another. This is the danger of living beside Proxima Centauri. The star may look like a steady red lamp fixed above the same landscape. In reality, its magnetic surface can produce sudden eruptions faster than a human team can respond. Astronomers discovered how relentless that activity might be by examining observations from the Atacama Large Millimeter and Submillimeter Array, known as ALMA. During about 50 hours of data, researchers identified 463 flare events. That averages more than 9 events per hour within the observed dataset. These limited observations do not prove 9 flares occur every hour forever. They show that danger may include a crowded background of brief events, not only rare explosions. Many lasted between roughly 3 and 16 seconds. Their estimated energies range from about 10 to the 24th ergs to 10 to the 27th ergs, spanning 3 orders of magnitude. The strongest released roughly 1,000 times more energy than the weakest. To understand why, look beneath the visible glow. Proxima Centauri contains electrically charged gas called plasma. As that plasma moves, it carries and twists magnetic fields. Different regions can pull the field in opposing directions. Energy builds inside the distorted structure. The process is similar to twisting several rubber bands together. At first, they bend and store tension. Continue pulling, and the arrangement becomes unstable. When the bands slip or snap into a new position, their stored energy is released almost instantly. On a star, the magnetic field does not behave exactly like rubber, but the useful principle remains. During magnetic reconnection, field lines break from one configuration and reconnect in another. Magnetic energy becomes heat, accelerated particles, and radiation. The event can be short. Its consequences may not be. A flare is not one thing traveling through space. It can produce visible light, ultraviolet radiation, X-rays, millimeter emission, and streams of energetic particles. Each component interacts with a planet differently. Visible light may brighten the surface and provide an obvious warning. Ultraviolet radiation can break molecular bonds and alter atmospheric chemistry. X-rays can heat and ionize the upper atmosphere. Millimeter waves allow astronomers to study energetic electrons and magnetic activity that optical observations may miss. High-energy particles add another problem. Unlike light, charged particles follow magnetic fields and may arrive on different timescales. If they reach the planet, they can penetrate equipment, disturb electronics, increase radiation exposure, and drive chemical reactions in the atmosphere. Watching only visible light would therefore be like monitoring a storm by measuring brightness while ignoring wind, pressure, and lightning. One instrument can report part of the event. It cannot describe the entire threat. For settlers, the first challenge is detection. A warning system would combine telescopes watching the star with instruments around the planet and sensors inside the habitat. A change in one wavelength might trigger automatic procedures before operators understand what happened. External work could stop. Rovers could enter protected modes. Sensitive circuits could disconnect. Crew members might move towards shelters surrounded by water, soil, or equipment that provides additional shielding. But 3 seconds leaves almost no time. The safest response would already be built into the settlement. Doors would close automatically. Data would be copied across isolated systems. Power controllers would prevent a damaged section from pulling the entire electrical network down with it. The atmosphere, if Proxima b has one, would also react. Ultraviolet light can split oxygen-bearing molecules. Some reactions build ozone, while others destroy it. X-rays and extreme ultraviolet radiation can strip electrons from atoms and molecules, ionizing the upper atmosphere and changing its temperature, circulation, and escape. Ozone matters because it can absorb dangerous ultraviolet radiation before that energy reaches the ground. Yet an ozone layer is not permanent armor. Its survival depends on atmospheric composition, production rates, chemical destruction, and the frequency of stellar events. This does not mean one ordinary flare strips away an entire atmosphere. Atmospheric loss is gradual. A heavier planet holds gas more strongly, while light particles escape more easily. Temperature, magnetic fields, stellar wind, chemistry, and volcanic replacement can all change the outcome. The honest question is not whether one flash blows the sky away. It is what happens after millions of flashes. Small events can become dangerous through repetition. Each may heat only part of the upper atmosphere or disturb only a fraction of the ozone. But if the next event arrives before the system recovers, damage can accumulate. The same principle applies inside the settlement. One radiation spike may not destroy a sensor, but hundreds may degrade it. Frequent shutdowns could interrupt farming lights, cooling pumps, instruments, and communications. Correctable memory errors could eventually overwhelm weak redundancy. Human exposure also accumulates. Ionizing radiation can damage DNA directly or create highly reactive molecules inside tissue. The body repairs much of that damage, but repair is not perfect. Risk depends on dose, particle type, shielding, tissue, and time. The crew would therefore fear two kinds of event. The first is the enormous flare that exceeds every design assumption. The second is the event too small to become famous, but common enough to keep systems under constant strain. After 50 hours, the monitor records warning number 463. No window shatters. No fire crosses the sky. Yet, filters work harder, electronics restart, and uncertainty enters every decision. The star does not need to destroy the colony in one explosion. It only needs to prevent the colony from fully recovering before the next alarm. Still, hundreds of flares cannot tell us whether the surface is exposed. Between the star and the ground may lie a protective atmosphere, a damaged remnant, or almost nothing at all. That unseen layer will decide whether Proxima b absorbs the assault or passes it directly to everything below. The pressure reading refuses to settle. The sensor reports only noise. That silence could mean the instrument is damaged. It could mean the air is too thin to measure. Or it could mean the crew has crossed 4.24 light years to find a planet whose protective sky disappeared. To determine which answer is possible, scientists must reconstruct a history. An atmosphere is never motionless. Molecules collide, rise, cool, react, and sometimes escape. On Earth, gravity holds most gases close, while the magnetic field reduces some effects of the solar wind. Proxima b may face the same processes. The first escape mechanism begins with heat. Extreme ultraviolet radiation and X-rays are absorbed high above the surface. Their energy heats the upper atmosphere. Light atoms and molecules begin moving faster. If some gain enough speed to overcome the planet's gravity, they escape into space. It is a loss from the outermost layers. Under intense heating, the upper atmosphere can expand, making more gas vulnerable. The second mechanism begins with ionization. High-energy photons strike atoms or molecules and remove electrons. The remaining particles carry positive electric charge. Once charged, they respond not only to gravity, but also to electric and magnetic fields around the planet. The third mechanism follows. Electrons are much lighter than ions, so they can escape more easily. As negative charge leaves, an electric field develops. That field can pull positively charged ions upward behind the electrons. The process is called polar wind on Earth. The fourth mechanism comes from outside. Proxima Centauri releases a stream of charged particles called stellar wind. Energetic particles associated with stellar activity may strike the upper atmosphere, transfer momentum, trigger chemical reactions, and help remove ions. Repeated interactions can change both the amount of gas and its composition. None of these mechanisms guarantees a bare planet. Their strength depends on atmospheric chemistry, planetary gravity, stellar history, magnetic geometry, and the supply of new gas from below. But one influential model showed how serious the risk could be. In 2017, NASA researchers modeled an Earth-like atmosphere at the orbit of Proxima b. They gave the simulated planet Earth's atmospheric composition, gravity, and magnetic field, then exposed it to radiation conditions expected near Proxima Centauri. In parts of that study, atmospheric escape was calculated to occur up to 10,000 times faster than it does on Earth. The researchers examined two limiting magnetic conditions. Depending on how easily particles could escape, an amount of gas comparable to Earth's entire atmosphere could be lost in roughly 100 million years to 2 billion years. Both timescales are short compared with the age of the system, yet the result is not a measurement of Proxima b's atmosphere. No instrument sampled its air. The model used Earth as a representative world because crucial properties of the actual planet remain unknown. Change the initial atmosphere, magnetic field, internal activity, or early stellar environment, and the outcome may change. That distinction is essential. A model is not a photograph of the past. It is a controlled test of physical assumptions. It tells scientists what could happen if those assumptions are close to reality. Proxima b may possess ways to replace lost material. Volcanoes can release water vapor, carbon dioxide, sulfur compounds, and other gases stored inside a planet. Molten rock rising from the mantle can transport volatile material toward the surface. Large impacts early in the planet's history might add gases or remove them. Chemical reactions between rock, ocean, and air can lock molecules away and release them later. Atmospheric survival is therefore an accounting problem. Gas leaves at the top, gas may return from the interior. The final balance depends on which flow remains larger across billions of years. A magnetic field complicates that balance rather than solving it automatically. People often imagine magnetism as an umbrella that redirects every harmful particle. Real magnetic fields have shapes. Some field lines close around a planet, others open towards space. Charged particles may be deflected, trapped, accelerated, or guided into the upper atmosphere near magnetic poles. Earth's field provides important protection, but it does not stop all atmospheric escape. Venus has no global Earth-like magnetic field and still retains an extremely thick atmosphere. Mars once had more air, yet today its atmosphere is thin. Magnetism matters, but gravity, chemistry, stellar exposure, and geological replacement matter with it. Inside the lander, the crew cannot choose the result it prefers. 3 versions of Proxima b remain physically valid. In the first, relentless radiation and particle exposure removed most of the original gases. The surface stands beneath an atmosphere so thin that it cannot distribute heat effectively or maintain stable liquid water across broad regions. Every human breath must come from a sealed tank. In the second, enough atmosphere survived or was replaced to produce moderate pressure. Winds carry energy away from the illuminated hemisphere. Clouds and perhaps an ocean help control temperature. Some locations might permit liquid water, although radiation and air chemistry could still make the surface unsafe. In the third, Proxima b retained or rebuilt a massive atmosphere. Pressure is high, heat moves efficiently, but strong greenhouse warming changes the climate. The planet may avoid a frozen night side, while becoming far hotter than a simple habitable zone label suggests. All 3 worlds share the same measured orbit. All can fit inside the uncertainties. That is the verdict of the first examination. The evidence does not reveal one Proxima b. It permits several. The pressure display produces a number. No one cheers. A single reading must be checked against temperature, instrument calibration, weather, altitude, and composition. Even if gas surrounds the lander, the crew still does not know whether it can protect them, poison them, freeze them, or overheat them. Survival cannot be planned around the most hopeful version. The settlers must now enter each possible planet in turn, beginning with the harshest case, a world where the sky is already gone. The outer hatch opens onto pressure lower than any human lung can use. There is no wind, no moving cloud, no air carrying warmth from the red-lit ground toward the permanent night. Dust disturbed by the lander rises briefly, follows clean ballistic arcs, and falls without drifting sideways. This is the most severe version of Proxima b, an exposed surface where the environment reaches every weakness. The first danger is not simply the absence of oxygen. Without sufficient atmospheric pressure, liquid water becomes unstable. Water can exist as ice, vapor, or liquid, but pressure helps determine which state survives. At very low pressure, exposed ice can pass directly into vapor through sublimation. Liquid released from a damaged pipe may begin boiling even when it is not hot, because boiling depends on pressure as well as temperature. The crew could watch a leak freeze and vanish at the same time. Rapid evaporation removes heat, cooling part of the water into ice, while vapor escapes above it. What looks like a small plumbing failure becomes a loss of air, heat, and the colony's most valuable chemical resource. Ice might remain in permanently cold regions, beneath soil, or inside minerals, but a dark deposit seen by radar would not automatically be a lake. To keep liquid water exposed for long periods, the planet would need suitable pressure, temperature, dissolved material, or protection beneath the surface. The temperature map would also become extreme. Rock beneath fixed starlight absorbs energy continuously. Rock on the night side loses infrared energy to space, with no substantial atmosphere to circulate heat and no confirmed ocean to carry it. Conduction through the ground becomes one of the few ways energy can move between hemispheres. Rock conducts heat far too slowly to equalize an entire planet. Imagine placing one end of a long iron bar in a fire while the other remains inside a freezer. Heat travels through the metal, but the two ends can still maintain very different temperatures. Enlarge that bar to planetary dimensions and replace iron with fractured rock. The contrast becomes harder to erase. The boundary between light and darkness might appear attractive. There, the star stays near the horizon, and direct heating is weaker than at the substellar point. On an airless world, that conclusion is too easy. A lower angle of light does not create breathable pressure, stop radiation, or guarantee moderate ground temperatures. Hills can cast permanent shadows only a short distance from illuminated slopes. One side of a ridge may absorb red light, while the other radiates into darkness. A settlement could face severe temperature changes across distances small enough to walk. Engineering would begin below ground. Several meters of local soil could provide mass between the crew and energetic particles. Habitats might be placed inside excavated chambers, natural lava tubes if they exist, or trenches coated with compacted material. Water tanks could surround sleeping quarters, placing a necessary resource where its hydrogen also helps slow some radiation. But shielding creates its own burden. Soil must be dug, transported, inspected, and supported. Abrasive grains can enter joints and seals. Machinery working outside needs lubrication that survives vacuum, temperature extremes, and radiation. Every excavation vehicle becomes part of life support because a broken shielding system cannot be replaced by stepping outdoors with a shovel. Power becomes equally unforgiving. Solar equipment on the illuminated hemisphere could receive continuous starlight, but Proxima Centauri is dimmer and redder than the sun. Panels would need to match that spectrum, remain clean, and survive stellar activity. A cable carrying electricity toward a sheltered region could cross sharp thermal gradients. Repeated expansion and contraction might fatigue connections. Nuclear power could provide steady energy independent of local light. Yet reactors require cooling, control systems, shielding, and maintenance. Waste heat cannot be carried away by outside air. It must move through coolant loops to radiators, which then release infrared energy into space, damage a radiator, and the habitat may overheat while the surrounding landscape remains frozen. Sound requires matter through which pressure waves can travel. A damaged pump might shake the ground without producing a voice in the open. An astronaut striking a tool against a metal support could feel vibration through a glove, but hear almost nothing through the environment. Communication would depend on radios and physical contact. Fire would behave differently too. Nothing burns in external vacuum without its own oxidizer. Inside the habitat, however, fire remains dangerous because the colony must carry oxygen. Smoke cannot be released by opening a window. Contaminated air must be filtered, isolated, or sacrificed along with an entire compartment. The absence of an atmosphere would simplify one uncertainty while worsening every daily task. Weather would no longer threaten antennas. There would be no atmospheric corrosion or storm pressure. Yet the colony would receive no free temperature regulation, no useful gas, no shielding from ultraviolet light, and no medium for parachutes or aircraft. Landing would rely on propulsion from beginning to end. Every kilogram of cargo would require controlled deceleration. Dust accelerated by rocket exhaust could damage engines, sensors, radiators, and nearby structures. Future landings might threaten the settlement they were intended to supply. A bare surface would not mean a useless planet. Rock may contain oxygen bound inside minerals. Subsurface ice could provide water. Metals, silicon, and other materials might support construction. With enough energy and industrial equipment, settlers could extract resources rather than carry every kilogram from Earth. But extraction is not discovery. A deposit must be located, sampled, processed, and purified. The first colony would need machines capable of building the machines that make independence possible. The crew looks across a landscape that offers matter, but no mercy. Survival is still possible, provided every habitable space remains manufactured and every failure is contained. Yet if the pressure sensor detects real air instead, danger does not disappear. It changes form, because the same gases that protect water and move heat can also transform the planet into a pressure vessel warmed beyond human limits. The second atmospheric test returns a measurable pressure. For the first time, the crew can imagine wind moving over the hull. Gas surrounds the lander, carries heat, and presses against every external surface. The number alone proves almost nothing. An atmosphere can make Proxima B more stable, more temperate, and more capable of holding liquid water. It can also produce crushing pressure, corrosive chemistry, violent circulation, or greenhouse warming. The important question is not whether air exists. It is how much exists, what it contains, and how it behaves beneath permanent red light. Atmospheric molecules are pulled downward by gravity. Their combined weight creates force against the ground. Add more gas, and surface pressure generally rises. Change gravity, and the same atmospheric mass can produce a different pressure. Because Proxima B's radius and surface gravity have not been measured directly, even estimating the amount of gas from pressure would require care. Pressure protects liquid water in one specific way. It raises the conditions under which water can remain liquid instead of boiling into vapor. But pressure alone does not make an ocean. Temperature and composition still matter. A high-pressure planet can be frozen, overheated, or chemically hostile. The gases also move energy. Near the substellar point, the surface absorbs radiation and warms the air above it. That air expands, becomes less dense, and rises. At higher altitude, it flows toward colder regions. On the night side, it loses energy, descends, and returns near the surface. This circulation can operate like a planetary conveyor, continually carrying energy away from the fixed source of light. The thicker the atmosphere, the more material may be available to transport heat. But the relationship is not a simple rule in which more air always creates a better climate. Nitrogen does not strongly absorb infrared radiation by itself under ordinary planetary conditions. Yet, it can still influence climate. It adds pressure, broadens the absorption behavior of other gases through molecular collisions, and provides mass for atmospheric circulation. It can help distribute heat without acting as the main greenhouse gas. Carbon dioxide behaves differently. The surface absorbs stellar energy and emits energy upward as infrared radiation. Carbon dioxide absorbs portions of that outgoing infrared energy, then emits energy in different directions. Some returns downward, reducing the rate at which the surface loses heat to space. This greenhouse effect is natural and essential on Earth. Too little greenhouse warming could allow water to freeze across much of Proxima b. Too much could push surface temperatures far above a useful range. Think of a winter blanket. If it is too thin, body heat escapes and the sleeper remains cold. If it is too thick for the room, heat accumulates and sleep becomes uncomfortable. The blanket does not create heat. It changes how quickly heat escapes. Greenhouse gases perform a related role for a planet, although through radiation rather than fabric. Warmer air can generally contain more water vapor, because water vapor is itself a greenhouse gas. Initial warming can allow more vapor to enter the atmosphere, producing additional warming. Cooling can reverse part of that cycle as the water condenses. On a synchronously rotating world, clouds may gather over the substellar region where heated, moist air rises. Some climate simulations show thick clouds reflecting enough stellar energy to prevent severe dayside warming. That result expands the range of incoming energy compatible with temperate conditions in those models. But a simulated cloud is not an observed cloud on Proxima b. Modelers choose assumptions about pressure, gases, oceans, rotation, surface reflectivity, and cloud physics. The computer then calculates how energy and matter respond, change the starting conditions, and the climate can move toward another stable state. The night side introduces a critical test. If air cools enough there, some gases may condense onto the surface. Carbon dioxide can freeze under suitable temperatures and pressures. As gas leaves the atmosphere, pressure falls. Lower pressure weakens heat transport, allowing more cooling and further condensation. This feedback can contribute to atmospheric collapse. A sufficiently dense atmosphere may resist that outcome by delivering heat faster than the night side can remove it. Winds do not need to make both hemispheres identical. They only need to keep critical gases above their condensation thresholds. Permanent heating on one side and cooling on the other create persistent pressure differences. Air accelerates in response, while planetary rotation influences its path through the Coriolis effect. If Proxima b rotates once every 11.2 Earth days, that influence would differ from Earth's. Circulation could form broad cells and high-altitude flows rather than familiar weather patterns. Settlers could not select a base using average temperature alone. A location with mild ground conditions might face constant winds. A sheltered basin might collect dense or toxic gas. High terrain could experience lower pressure and stronger radiation. Atmospheric chemistry near the surface could change with altitude. Volcanic release, or reactions driven by stellar ultraviolet light. Humans need suitable oxygen partial pressure, not merely oxygen molecules somewhere in the spectrum. Too little provides inadequate oxygen to tissues. Too much increases fire risk and can damage the body over time. Carbon dioxide becomes harmful at concentrations far below the amount required to dominate an atmosphere. Unknown trace gases could poison crews or attack equipment. The settlement would therefore remain sealed. Still, no responsible crew would open the habitat until repeated local measurements had mapped pressure, composition, microbes if any, dust, and weather. An atmosphere could be Proxima B's greatest protection and its most deceptive hazard. A thin layer may fail to preserve water. A moderate layer may redistribute heat. A massive layer may protect the night side, while overheating the entire surface. What pressure is enough to defend liquid water, move warmth through permanent darkness, and shield the ground without turning the world into a greenhouse too severe for settlement? Air can carry heat rapidly. If an ocean lies beneath it, however, water will move that energy more slowly, store it longer, and redraw every location the crew currently considers safe. The probe drills through a sheet of ice and finds salt water below. That discovery would change the mission immediately. Water can store far more heat than rock or air. It can transport energy across enormous distances. It can feed clouds, shape winds, dissolve gases, and support chemistry that dry land cannot sustain. But an ocean is not automatically a second Earth. On Proxima b, the location, depth, salinity, and circulation of that water could decide whether the planet remains temperate, freezes into separate hemispheres, or enters a climate no human settlement can control. Water has a high heat capacity. It requires significant energy input to warm, and it releases that energy slowly as it cools. This is why coastal regions on Earth often experience smaller temperature changes than continental interiors. The ocean absorbs heat during warm periods and returns part of it when the surrounding air cools. On a planet beneath fixed starlight, that buffering could operate continuously. Surface water, near the substellar point, would absorb energy from Proxima Centauri. Winds would push across it. Temperature differences and salinity differences would change the water's density. Warmer water would tend to remain near the surface, while colder or saltier water could sink. Those density contrasts could drive currents toward the night side and return deeper water toward the light. The result might be an oceanic circulation system, capable of carrying energy farther than the atmosphere alone. Yet, planetary rotation would shape every current. On Earth, rotation deflects moving air and water through the Coriolis effect, helping organize large gyres and boundary currents. Proxima b may rotate once every 11.2 Earth days. Its slower spin could produce broader circulation patterns, while continents, seafloor depth, and coastlines would redirect them in ways no present observation can reveal. If land surrounds the substellar ocean, currents may struggle to export heat. If a global ocean connects the illuminated and dark hemispheres, water may carry energy across the twilight boundary. Shallow seas respond quickly. Deep oceans store more heat, but their deepest layers may circulate slowly enough to trap carbon and nutrients for long periods. Ice adds another layer of uncertainty. Water expands when it freezes and forms a surface layer less dense than the liquid below. That floating ice can insulate the ocean beneath it. On the night side, kilometers of ice might cover liquid water kept warm by transported heat, pressure, or geothermal energy from the planet's interior. Settlers would need to drill, keep the opening from refreezing, pump brine upward, remove salts, and prevent unfamiliar dissolved chemicals from contaminating life support systems. Clear ice could still contain perchlorates, metals, acidic compounds, or microorganisms with chemistry dangerous to Earth biology. Near the day side, the opposite problem could develop. Strong heating increases evaporation. Water vapor rises, cools, and forms clouds. Those clouds may reflect incoming light and stabilize the climate, especially if they remain concentrated around the substellar point. This negative feedback appears in several climate simulations of slowly rotating worlds. As heating rises, cloud cover can rise with it, returning more stellar energy to space. But clouds also absorb and emit infrared radiation. Their altitude, thickness, particle size, and location determine whether cooling or warming dominates. A bright cloud deck can protect the surface. High, thin clouds can reduce heat loss. No telescope has yet mapped either pattern on Proxima b. Water vapor itself can become dangerous. If the lower atmosphere warms, more water evaporates. Additional vapor strengthens greenhouse warming, allowing still more evaporation. Under extreme conditions, the upper atmosphere becomes moist. Ultraviolet radiation can then split water molecules. Light hydrogen escapes more easily, leaving oxygen behind or allowing it to react with surface rock. A world can therefore lose an ocean without losing every trace of oxygen. This matters because future astronomers might detect oxygen and feel immediate excitement on Earth. Most atmospheric oxygen is associated with life. Around an active red dwarf, however, intense early radiation could remove water and create oxygen through non-biological processes. Oxygen would be evidence requiring explanation, not a final verdict. Carbon dioxide would also move between ocean, air, and rock. Water dissolves carbon dioxide. Chemical weathering can transform it into dissolved ions and eventually carbonate minerals. Volcanic activity can return carbon dioxide to the atmosphere on Earth. This long carbon cycle helps regulate climate over geological time. Proxima b may not have the same machinery. Tidal locking does not stop plate tectonics, but the planet's interior, crust, water content, and heat flow remain unknown. If geological recycling is weak, carbon could become trapped in rock. If volcanism is intense, greenhouse gases could accumulate faster than weathering removes them. The ocean could then become acidic, hot, or hidden beneath pressure. Deep water produces pressure through its weight. At sufficient depth, water can form high-pressure ice phases even when temperatures are above ordinary freezing. These forms are denser than familiar ice and may develop at the bottom of very deep oceans. A layer of high-pressure ice could separate liquid water from rocky seafloor, interrupting chemical exchange that may be important for habitability. So even a global ocean can deny settlers easy minerals, stable chemistry, or accessible land. The crew cannot celebrate a blue reading on a sensor. It must ask where the water came from, how rapidly it circulates, what lies beneath it, and whether the star is slowly removing it. A surviving ocean would be one of the strongest arguments that Proxima b retain useful conditions. It could soften temperature extremes and preserve reserves beneath ice. It could also produce storms, corrosive salt, powerful greenhouse feedbacks, and coastlines that shift as ice migrates between hemispheres. After the drill withdraws, the sample chamber warms, ice becomes liquid, dissolved gas escapes in bubbles, and instruments begin separating its chemistry. Water has been found, safety has not. The next decision must be made on a planetary map where permanent noon, endless night, moving air, buried ice, and stellar radiation overlap. Somewhere among those hazards may be the least dangerous place to build. The first settlement is not built where the temperature is most comfortable. It is built where several dangers become survivable at the same time. On Proxima b, those two locations may not be identical. A mild temperature reading can hide intense radiation, unstable ground, constant wind, scarce water, or a power system stretched across hundreds of kilometers. Choosing a site means balancing failures that do not appear on the same map. The obvious candidate is the twilight region. This boundary separates the hemisphere facing Proxima Centauri from the hemisphere turned away. The star would sit near the horizon, providing less direct heating than at permanent noon, while offering more energy than the night side receives. It sounds like a narrow ring of eternal sunset. If the atmosphere moves heat efficiently, habitable temperatures could extend into both hemispheres. If the atmosphere is thin, the transition may become severe across short distances. Mountains change illumination, clouds alter heating, ocean currents move warmth. Even a small orbital eccentricity or non-synchronous rotation could shift the thermal pattern over time. The useful zone must therefore be measured, not assumed. Survey aircraft would help only if atmospheric density and chemistry allowed flight. Rovers could map pressure, radiation, terrain, ice, and temperature, but each vehicle would move slowly across a planet. Orbital instruments could scan broad regions, yet clouds and limited resolution might hide local hazards. Radiation would push the settlement away from exposed terrain. A thick atmosphere could absorb much ultraviolet radiation and reduce some particle exposure. Without that protection, planners would favor caves, lava tubes, cliffs, or ground that can be excavated and covered. But underground does not always mean safe. A lava tube may contain unstable ceilings, sharp debris, trapped gases, or no convenient route for heavy equipment. A deep trench can shield radiation, but collect dense toxic gases if an atmosphere exists. Frozen ground may provide water while expanding, cracking, or settling as machinery adds heat. Power pulls the colony toward the light. Solar arrays placed farther onto the dayside would receive stronger and more reliable illumination. Habitats placed nearer darkness may gain cooler conditions and natural terrain shielding. Connecting them requires transmission lines, maintenance roads, storage, and backup systems. High voltage lines lose energy and need insulation suited to local pressure, dust, and temperature. Buried cables resist radiation and wind but are harder to inspect. Surface cables remain accessible but face erosion, thermal stress, and impact damage. Wireless power across large distances would introduce conversion losses and precise pointing requirements. A colony cannot depend on one illuminated field. Solar generation would be divided into separate farms. Batteries or other storage would cover interruptions. Nuclear units could provide steady baseline power. Critical habitats would maintain isolated emergency supplies capable of running air circulation, carbon dioxide removal, medical equipment, and communications after the main grid failed. Water pulls the settlement in another direction. Nightside ice may be abundant but deeply frozen. Dayside water may be easier to pump but vulnerable to evaporation, contamination, or climate instability. A twilight glacier could appear ideal until measurements reveal it is moving, salty, or resting above fractured ground. 1 cubic meter has a mass of roughly 1,000 kilograms under familiar conditions. A settlement using water for drinking, hygiene, agriculture, industry, radiation shielding, and oxygen production must move and recycle large quantities. A distant source creates dependence on pumps and pipes, whose failure can stop the entire colony. Food production imposes quieter requirements. Greenhouses need light, temperature control, carbon dioxide, nutrients, water, and protection from contamination. Natural red starlight might support photosynthesis for suitable organisms, but crops selected on Earth may not use the spectrum efficiently. Artificial lamps provide control while consuming electricity and producing heat that must be removed. Placing farms beside power generation shortens electrical connections. Placing them beside habitats shortens food, water, and air loops. Separating them reduces the chance that one fire or pressure loss destroys everything. Engineers would divide the colony into compartments and districts. Sleeping areas, farms, reactors, workshops, laboratories, and storage would remain connected but capable of isolation. 2 routes would reach every critical resource. No single tunnel, transformer, or airlock would be allowed to separate the crew from water or shelter. The star itself influences site selection. A settlement beneath direct view of Proxima Centauri can monitor flares without terrain-blocking instruments. Yet a crater wall or ridge may provide valuable shielding near the horizon. Observatories could stand separately on high ground, while habitats remain buried behind rock. Communications with Earth add little help. A message takes more than 4 years to arrive. The answer needs more than 4 years to return. A question about a cracked foundation could wait over 8 years for a response, long after the crew repaired it or died from it. The final site might lie slightly inside the night side, where nearby rock blocks the fixed star and the atmosphere delivers enough heat to prevent extreme cold. Power could arrive from solar fields beyond the horizon, while buried reactors support emergencies. Ice deposits could supply water. Elevated relays could maintain contact with surface machines. The safest location may instead be a high plateau under permanent light, a coastal basin moderated by ocean currents, or a deep volcanic tube far from both water and solar power. Proxima b offers no universal address called the habitable zone. Habitability changes from kilometer to kilometer. The crew marks 3 candidate sites. None wins every category. 1 has water, but weak ground. 1 has excellent power, but high radiation. 1 offers shelter, but lies far from usable minerals. They choose the site where no single loss becomes immediately fatal. That principle matters more than pleasant weather. A colony does not die because its average conditions are poor. It dies when one broken link removes air, water, power, cooling, food, or shelter faster than people can restore it. And once construction begins, the greatest threat may no longer come from the planet. It may begin inside the network designed to keep everyone alive. The carbon dioxide monitor rises by less than 0.1%. No alarm sounds. The crew continues working. Plants remain illuminated. Water flows through the recycling system, and every pressure gauge stays inside its approved range. 6 hours later, 2 astronauts report headaches. The increase seems minor, but a sealed settlement cannot treat any unexplained chemical change as minor. Outside air cannot be brought through an open vent. Every breath enters a network that must remove waste, restore oxygen, control humidity, filter contaminants, and return usable gas to occupied rooms. The colony does not merely contain life support machines. The colony is one life support machine. Human beings consume oxygen and release carbon dioxide. Crops absorb part of that carbon dioxide under light, but their contribution varies with species, growth stage, temperature, and illumination. Microorganisms inside waste processors consume or produce gases, plastic, insulation, lubricants, cleaning agents, and heated electronics release trace chemicals. Every compartment changes the atmosphere. Mechanical scrubbers must remove carbon dioxide faster than people, and equipment add it. One possible system uses solid materials that selectively capture carbon dioxide when exposed to cabin air. The material is later heated or placed under lower pressure, releasing the concentrated gas so it can be stored, processed, or directed toward plant chambers. This creates a repeating cycle of adsorption and regeneration. A valve opens at the wrong time, a heater loses power, or dust blocks airflow, and the cycle becomes less effective. The unit may continue running while its actual removal capacity declines. Fans still turn. Indicator lights remain green. Only the atmospheric trend reveals that the settlement is slowly losing control. The crew activates the backup scrubber. Carbon dioxide begins falling, but the backup draws additional electricity. The power controller increases output from a local distribution unit. That unit produces more waste heat, forcing the cooling system to circulate fluid faster. Now, one atmospheric failure has become an electrical and thermal event. Inside a large settlement, systems cannot be separated neatly. Air processors need power. Power equipment needs cooling. Cooling loops need pumps. Pumps need control electronics. Electronics need stable temperature and radiation protection. Repair crews need breathable air while maintaining all of them. A failure travels through these dependencies. Engineers call this a cascading failure. The original fault may be small, but it forces other components into unusual operating conditions. Those components consume reserves faster, run hotter, or lose redundancy. If another problem appears before the network returns to normal, the colony enters a condition its designers never tested as a single scenario. On Earth, a building can lose ventilation and be evacuated. On Proxima b, evacuation means moving it to another sealed structure supported by related machinery. If the same software, filters, valves, or power architecture serve both locations, the supposed refugee may share the original weakness. True redundancy requires more than 2 identical machines. 2 pumps installed beside each other can both be damaged by one fire. 2 computers running the same software can both obey the same incorrect command. 2 air processors drawing electricity from one cable can stop together when that cable fails. Independence matters as much as quantity. Critical systems would need physical separation, different power paths, isolated controllers, spare sensors, and manual operating modes. Some backups might even use different technical principles. A chemical oxygen source, for example, could support an emergency shelter when the normal electrolysis system failed. But diversity introduces new complications. Different machines require different training, tools, replacement parts, and diagnostic procedures. A crew that understands one standardized pump may struggle to maintain 5 unrelated designs. The settlement must balance common equipment, which simplifies maintenance, against diverse equipment, which prevents one defect from disabling everything. Sensors create another weakness. A control system does not respond to the real atmosphere directly. It responds to measurements. If a carbon dioxide sensor drifts upward, the scrubber may work harder than necessary. If it drifts downward, dangerous concentrations may develop while the display looks normal. Multiple sensors can compare readings, but agreement does not always prove accuracy. Devices produced in the same batch may age similarly. Radiation may affect them together. A contaminated sampling line can feed identical bad air to several perfect instruments. The crew therefore checks machines against physical standards and independent methods. Portable detectors move between compartments. Gas samples enter laboratory instruments. Human symptoms become supporting evidence, although relying on headaches or confusion means waiting too long. The colony must also control oxygen. Electrolysis can split water into hydrogen and oxygen. The oxygen returns to the habitat. Hydrogen may be stored, used in chemical processes, or combined with captured carbon dioxide to produce water and methane. This sounds like a closed loop, but no physical loop is perfectly closed. Small amounts of gas escape through seals. Water remains trapped in waste or manufacturing products. Filters accumulate material. Chemical reactions form compounds that are difficult to recover. Every cycle loses something, or changes its quality. A settlement survives by keeping those losses below its ability to replace them. Plants help, yet farms introduce living uncertainty. A crop disease may move through genetically similar plants. A nutrient imbalance can reduce growth before leaves show obvious damage. Pollination can fail. Fungi can spread through moist ventilation ducts. A lighting failure lasting several hours may not kill mature plants, but it can disturb growth schedules and reduce future harvests. Agriculture also competes with people for water, power, cooling, space, and attention. During an emergency, commanders might reduce farm lighting to preserve energy for air circulation. That decision solves the immediate crisis while lowering food production weeks later, increase lighting afterward, and the farm creates additional heat that the recovering cooling system must remove. There are no isolated decisions. Food reserves provide time, but stored nutrition deteriorates. Some vitamins break down during long storage. Packaging can fail. Insects or microbes may enter supplies. Seeds remain compact, but seeds cannot replace the calories of a failed harvest overnight. The settlement requires overlapping reserves measured in months, not days. Water offers the clearest example of hidden dependence. Urine, humidity, washing water, and industrial wastewater can be processed and reused. Distillation, filtration, oxidation, and chemical treatment remove different contaminants. Yet, concentrated brine remains. Membranes foul. Catalysts lose performance. Even a recovery rate of 98% would lose 2 liters from every 100 processed. Across years and a growing population, that missing fraction becomes enormous unless local ice or minerals replenish it. The crew traces the original carbon dioxide rise to a warped valve inside the regeneration assembly. The component weighs less than a human hand. Its failure activated 2 air units, 3 additional pumps, a cooling branch, emergency batteries, and dozens of procedures. Nothing dramatic broke. That is what makes the incident frightening. The colony survives because technicians identify the fault before reserves fall too far. They replace the valve, test the scrubber, recharge the batteries, and restore normal circulation. Then the damaged part is placed in a storage container. There is no supply ship behind them, no warehouse on another continent. The replacement came from a limited inventory assembled before departure, and the inventory now contains 1 fewer valve. For the colony to survive longer than its stockpile, it must learn to manufacture precision from an alien world. The replacement valve fails after 19 years. By then, several children born on Proxima b are adults. They have never seen Earth except through recordings. They know its blue oceans, changing sky, and moving sun as images from a world no spacecraft can reach within their lifetime. They also know that the storeroom contains no third valve. A permanent colony cannot remain a collection of imported machines. Every bearing eventually wears, every seal becomes brittle, every filter accumulates contaminants. Radiation damages electronics, repeated heating weakens cables, and lubricants slowly change. Reliability delays failure. It does not abolish it on Earth. A broken industrial component belongs to a global system. Raw material may come from one country, semiconductor equipment from another, software from a third, and final assembly from a fourth. Trucks, ships, aircraft, mines, factories, universities, and power grids support the small object delivered to a maintenance worker. Proxima B has none of that infrastructure at first. The crew may possess detailed manufacturing files, but information cannot turn rock directly into a working component. Material must be found, extracted, separated, purified, shaped, treated, measured, and tested. Each stage requires equipment that also needs maintenance. Consider a simple steel bolt. Iron-bearing rock must be mined. The useful minerals must be separated from waste. Oxygen and other elements must be removed through chemical or thermal processing. Carbon and alloying elements must be controlled. The metal must be cast, rolled, cut, threaded, heat-treated, and inspected. A bolt that looks correct may still fail. Its internal structure can contain cracks. Incorrect heat treatment can make it too soft or brittle. Threads outside tolerance may loosen under vibration. Corrosion can begin where the eye sees nothing. Now, replace the bolt with a pressure valve controlling breathable air. Its body must survive repeated stress. Its sealing surfaces require precise dimensions. Springs must retain predictable force. Polymers must resist local gases, temperature changes, radiation, and thousands of operating cycles. Sensors and actuators must respond at the correct moment. Printing its shape is only the beginning. Additive manufacturing can produce complex parts layer by layer. It reduces the need for specialized molds and can turn stored digital designs into physical objects. But printed metal may contain pores, residual stress, or uneven microstructure. The component may require machining, heat treatment, surface finishing, and non-destructive inspection. A colony capable of printing a valve must also verify that the valve will not kill anyone. Inspection could use ultrasound, X-rays, electrical testing, pressure chambers, microscopes, and repeated cycling. Calibration tools need their own reference standards. Those standards must remain accurate despite age, transportation, radiation, and local gravity. Measurement becomes a foundation of survival. If a machine tool is misaligned by a fraction of a millimeter, it can produce hundreds of parts that all appear usable and all fail early. If a pressure standard drifts, every sensor calibrated against it inherits the error. The settlement needs metrology, the science of reliable measurement. Technicians would preserve reference masses, electrical standards, dimensional gauges, chemical samples, and procedures for comparing instruments. Where possible, thus they would connect measurements to stable physical phenomena rather than one aging device. Electronics present an even greater challenge. Mechanical parts can sometimes be machined from local metal. Advanced semiconductor chips require exceptionally pure materials, controlled chemical processes, precisely deposited layers, and fabrication environments almost free of dust. Modern chips contain structures far smaller than anything an ordinary workshop can reproduce. The first colony would carry large inventories of processors, memory units, sensors, power components, and communication hardware. Designs might intentionally use older, larger electronic features that are easier to manufacture and more tolerant of radiation. Performance would be sacrificed for repairability. A slow computer that can be understood, replaced, and rebuilt may be more valuable than a powerful device whose production depends on an absent factory. Control software would need to run on several hardware types, so one discontinued chip could not paralyze the settlement. Software itself can decay without physically wearing out. Files become corrupted. Documentation becomes incomplete. Updates introduce errors. A control program written decades earlier may contain assumptions no living technician remembers. If knowledge survives only as code, the colony may know how to operate a machine without understanding why it behaves correctly. Every critical design, therefore, needs explanation, not merely instructions. Manuals must describe principles, failure modes, tolerances, materials, test procedures, and safe substitutes. Training cannot be limited to the crew who arrive from Earth. Each generation must learn enough physics, chemistry, medicine, agriculture, geology, and engineering to preserve the system. That creates a difficult educational choice. Children need broad knowledge because the colony is small, yet complex machines demand specialization. One person cannot become an expert surgeon, electrical engineer, crop scientist, metallurgist, and reactor technician at once. A population can lose a capability when a single specialist dies. The colony must train overlapping teams before expertise becomes scarce. Procedures should be recorded from multiple perspectives. Apprentices must perform real maintenance rather than only watch simulations. Emergency drills must include situations where the usual expert is unavailable. Knowledge stored in a database is not the same as knowledge held by a practiced hand. A manual may specify how tightly to fit a seal. An experienced technician recognizes the sound of a misaligned shaft, the smell of overheating insulation, or the faint vibration that appears before a bearing fails. These observations are difficult to convert into searchable text. Experience must be transferred while its owner is alive. The settlement also needs chemical independence. Local rock may supply iron, aluminum, silicon, magnesium, and oxygen. But deposits must be discovered and processed. Carbon, nitrogen, phosphorus, sulfur, and trace elements are essential for life and industry. A planet can contain an element while keeping it locked inside minerals that are expensive to refine. Energy determines what becomes usable. With abundant power, colonists can heat ore, split water, purify metals, recycle waste, and synthesize chemicals. With limited power, rich deposits may remain practically inaccessible. Mining equipment consumes energy before it produces any useful material, so industrial expansion initially places more strain on the colony. The settlers cannot wait until the imported inventory is almost gone. They must build workshops while spare parts remain available. They must test locally made components beside trusted originals. Early failures become lessons while backups still exist. Recycling systems must recover metals, polymers, nutrients, and electronic components before scarcity forces desperate improvisation. Nothing is thrown away casually. A damaged pressure tank becomes sheet metal. A failed circuit board yields connectors and rare elements. Human waste returns nutrients to agriculture after careful treatment. Broken tools become feedstock. Storage rooms slowly transform into material banks, organized by composition rather than original purpose. The new valve is not identical to the Earth-made component. It is larger because local machines cannot reproduce every tiny feature. Its actuator uses a simpler design. The housing contains Proxima B iron, mixed with imported alloy recovered from obsolete equipment. Engineers test it far beyond normal pressure, inspect its interior, and install it beside a second independent unit. When it opens, cabin air moves through machinery built on another world. That moment marks a deeper kind of arrival. The colony is no longer surviving only on objects carried from Earth. It has begun converting an unknown planet into the precise materials required for human life. But machines are only one inheritance that must endure. The people maintaining them will age, disagree, form families, and pass authority to descendants who never chose the mission. Their ability to remain one functioning society may determine whether any technical achievement survives. The first person born on Proxima B refuses an order from Earth. The instruction was transmitted more than 4 years earlier. When the settlement faced the different conditions and different leaders, by the time it arrives, the damaged reactor has been repaired, 2 council members have died, and the child named in the medical report has become an adult technician. The message is accurate. It is also obsolete. Distance has transformed communication into archaeology. Earth can send knowledge, warnings, and opinions, but it cannot govern events in real time. Every emergency must be resolved locally. Every law must be enforced by people living under it. Eventually, authority belongs to those who carry the consequences. That transition may be more dangerous than any broken valve. The original settlers accepted the mission voluntarily. They understood that return might be impossible. Their children accepted nothing. They inherited sealed habitats, strict work schedules, limited resources, and a planet where one careless action could endanger everyone. A person born inside the colony may ask a question no engineering manual can answer. Why must I spend my life preserving a mission chosen before I existed? The settlement cannot dismiss that question as selfish. Every society depends on cooperation. But Proxima B requires cooperation at an unusual level. On Earth, someone can leave a job, move to another city, or reject the goals of an institution. Inside a small extraterrestrial colony, withdrawing from essential work may affect air production, medical care, food, or power. Freedom still matters. So does the carbon dioxide scrubber. A stable society must protect individual choice without pretending every choice has only individual consequences. That balance will influence education, employment, reproduction, punishment, and political authority. At first, command may resemble a spacecraft hierarchy. During emergencies, clear authority saves time. One person orders a compartment sealed, a reactor shut down, or a crew evacuated. Debate can occur afterward. Permanent life cannot remain a continuous emergency. If commanders control housing, oxygen, food, medicine, employment, and reproduction indefinitely, technical necessity can become permanent authoritarian power. Yet a system requiring a public vote before every urgent repair could become dangerously slow. The colony needs separate modes of government. Emergency authority must be narrow, temporary, recorded, and reviewed. Long-term decisions need representation, transparent evidence, and a process for removing leaders. Life support engineers should be able to stop actions that create immediate physical danger, but they should not automatically control education, family life, or justice. Information must remain visible. If only a small technical group understands the colony's true reserves, that group can manipulate everyone else. Citizens need access to measurements of water, food, power, radiation, medical supplies, and industrial capacity. Uncertainty should be reported honestly rather than hidden to prevent panic. Trust built on false reassurance breaks at the worst moment. Resource rationing creates the first serious test. A crop disease reduces the expected harvest. Healthy adults can survive smaller meals temporarily, but children, pregnant women, patients, and workers performing heavy labor have different nutritional requirements. Dividing food equally may appear fair while producing unequal medical harm. The Council must decide according to need, contribution, risk, or some combination. Every choice creates resentment. If engineers receive larger portions because their work protects the habitat, other residents may see a privileged technical class. If everyone receives identical portions, critical maintenance workers may become physically unable to perform demanding repairs. If leaders secretly protect their families, political legitimacy can collapse in a single week. Justice is not an abstract luxury there. It is part of life support. Population planning becomes even more personal. A small colony cannot allow population to grow faster than food, housing, medicine, and power. It also cannot allow birth rates to fall so low that essential skills disappear as adults age. Each new child represents a human life, a future worker, years of education, and decades of resource consumption. No universal minimum population guarantees survival. Genetic diversity depends on the number of founders, their relationships, reproductive patterns, stored biological material, and events across generations. A settlement carrying frozen sperm, eggs, or embryos could preserve far more genetic variation than its living population alone. But a biological archive does not raise children. Families do. Restricting reproduction would create profound ethical conflict. Allowing unrestricted growth could exceed the colony's physical capacity. Assigning partners for genetic reasons would violate personal autonomy. The society needs voluntary planning, confidential medical counseling, long-term demographic models, and enough reserve capacity that every unexpected pregnancy does not become a political crisis. Genetic risk is only part of the problem. Children developing under different gravity may experience altered bone growth, muscle strength, balance, circulation, and vision. Proxima B's true radius is unknown, so its surface gravity remains uncertain. If gravity is substantially greater than Earth's, pregnancy and childhood could place additional strain on the heart and skeleton. If it is lower, bones and muscles may not develop for Earth-like conditions. There may be no safe experiment capable of answering every question before the first birth. Medical records therefore become essential across generations. Doctors must separate inherited conditions from environmental effects, nutritional deficiencies, radiation exposure, and small population statistics. A pattern seen in 3 children may signal a serious planetary effect or coincidence. Psychological health presents another quiet threat. The landscape never provides a normal sunrise. The star remains fixed if the planet is perfectly synchronized. The same terrain surrounds the settlement. Earth is not a destination for vacation or retirement. It is a delayed voice from the past. Circadian rhythms can be supported with artificial lighting, schedules, exercise, and private sleeping spaces. Those tools regulate biology. They do not remove grief, confinement, conflict, or the feeling of being trapped. People need more than survival tasks. They need music, sport, privacy, friendship, celebration, exploration, and work, whose value is not measured only in oxygen saved. Rooms dedicated to art may appear inefficient, until a population without meaning begins losing motivation, attention, and trust. Culture becomes protective infrastructure, so does disagreement. A society that punishes every challenge to authority may preserve order briefly while hiding mistakes. A society that permits evidence-based criticism can identify weak decisions before they become disasters. The colony needs people willing to question a reactor design, a medical diagnosis, and a political leader without being treated as enemies. The greatest danger is not conflict itself. It is conflict that cannot be resolved without damaging essential systems. No angry group can be allowed to control oxygen as leverage. No security force should have one switch capable of isolating political opponents from food or communications. Critical infrastructure must remain governed by procedures stronger than any faction. The first locally born commander eventually faces the settlement council. She argues that Earth's latest instruction should be preserved as expert advice, but not obeyed as law. The council agrees. Its decision is transmitted toward the solar system, where no response will return for more than 8 years. In that moment, the colony becomes politically independent through physics rather than revolution. It still carries Earth's languages, science, history, and mistakes, but its future will be decided beneath another star by people who understand that survival alone is not enough. They must build a society worth surviving for. The colony's oldest telescope turns toward Earth. Nothing resembling home is visible to the human eye. The sun appears as one star among many. Every ocean, city, forest, and person who remain behind occupies a point of light 4.24 light-years away. After decades of work, the settlement is still alive. That does not mean humanity could build it today. Proxima b remains a real planet, surrounded by profound unknowns. Astronomers know its approximate orbital period and minimum mass through the gravitational influence it exerts on its star. They know it receives an amount of stellar energy compatible with some habitable climate models. They do not know whether its surface contains oceans. They do not know its atmospheric pressure, exact radius, global magnetic field, geological activity, surface radiation, or present inventory of water. They do not know whether it possesses a moderate climate, a massive greenhouse atmosphere, or almost no atmosphere at all. Calling it potentially habitable describes a scientific possibility. It does not describe a prepared destination. The first obstacle appears before any crew leaves Earth. At the speed of Voyager 1, a journey across 4.24 light-years would require roughly 70,000 years. Voyager was not designed to travel toward Proxima Centauri, and its exact travel time is not a mission proposal. The comparison reveals the scale of the distance using hardware. Humanity has already operated beyond the planets. A human mission would require propulsion far beyond current crude capability. Nuclear systems, fusion concepts, antimatter proposals, laser-driven sails, and other advanced designs offer possible paths on paper or at experimental scales. Each faces a different combination of fuel, energy, mass, heat, reliability, and deceleration problems. Acceleration receives most of the attention. Stopping is just as important. A spacecraft crossing interstellar space at a significant fraction of light speed cannot arrive and simply apply ordinary brakes. It must carry propulsion capacity for deceleration, interact with magnetic or particle environments, or rely on infrastructure placed at the destination in advance. Infrastructure cannot be waiting unless earlier missions built it. High speed also changes small objects into major threats. Interstellar space is extremely sparse, but it is not perfectly empty. Gas atoms and dust grains striking a fast spacecraft can release intense energy, erode shielding, generate secondary radiation, and damage forward sensors. The faster the ship travels, the more severe those impacts become. Shielding adds mass. Added mass demands more propulsion energy. Larger propulsion systems require more structure, cooling, and protection. Every solution affects the rest of the vehicle. Then comes time. A multi-generational ship must recycle air and water, produce food, control disease, replace machinery, preserve knowledge, and maintain a stable population for longer than any closed human habitat has operated. A faster ship reduces those demands but increases the difficulty of propulsion, shielding, and stopping. There is no free route across the distance. Small robotic probes may arrive first. Laser-driven sails have been proposed for accelerating extremely lightweight spacecraft to a substantial fraction of light speed. A gram-scale probe is not a colony ship, but it could photograph planets, study magnetic conditions, and examine an atmosphere during a rapid encounter. Even that mission would face communication limits. A tiny transmitter must send data across more than 4 light-years. The signal weakens as it spreads. The probe needs power, accurate pointing, functioning instruments, and a way to survive interstellar impacts before delivering anything useful. A flyby lasting hours could answer questions accumulated over decades. It could also reveal that Proxima b is a terrible destination. That would not make the mission a failure. Discovering an airless, irradiated planet before launching humans would be one of the most valuable results imaginable. Robotic exploration exists to replace hope with evidence. A responsible pathway would proceed in stages. First, increasingly powerful telescopes would search for atmospheric gases, temperature contrasts, clouds, and signs of atmospheric loss. No single gas would prove habitability or life. Oxygen can arise through biological and non-biological processes. Carbon dioxide can support a stable climate or signal extreme greenhouse conditions. Water vapor can indicate accessible water or an atmosphere losing it to space. Multiple observations must agree. Second, robotic probes would directly examine the system. They could measure stellar particles, dust, magnetic fields, planetary mass, radius, and atmospheric composition with far greater confidence. Third, automated equipment might enter orbit or land. Machines could test local mining, power generation, construction, and fuel production before any person depended on them. They could bury shelters, store supplies, deploy reactors, and verify that critical systems work for years without human repair. Only then would a crewed mission become defensible. Even with preparation, settlers would not land on an untouched world carrying tents and optimism. They would enter an industrial site whose most important systems already possess backups: power, water extraction, communication, shielding, and environmental monitoring would need to function before the first human breath entered the habitat. The settlement would still remain an experiment without rescue. A medical crisis could not be answered by evacuation. A new pathogen, crop failure, reactor defect, or geological event might exceed every preparation. Earth could send information, but each exchange would consume more than 8 years. Colonization, therefore, requires a different definition of success. Planting a flag proves arrival. A permanent settlement must survive the exhaustion of imported parts, the death of its founders, political disagreement, reproductive transitions, environmental surprises, and the moment when Earth's instructions are no longer sufficient. It becomes successful only when people born there can maintain it without depending on a supply chain that does not exist. Could humans colonize Proxima b? Physics does not provide a simple prohibition. If the planet has usable materials, if advanced propulsion shortens the journey, if machines prepare the destination, and if humans create a truly self-sufficient industrial society, settlement may be possible. But every if hides decades or centuries of work. The greatest discovery is not that Proxima b resembles Earth. Current evidence does not justify that claim. The greater lesson is that distance removes every safety net civilization normally takes for granted. A planet does not need to be lifeless to be deadly. It does not need to be Earth-like to become useful, and it does not need to welcome humans for humans to survive there. The final transmission from Earth arrives during the colony's anniversary. It contains scientific updates, personal records, music, and images of a world none of the younger residents has visited. They watch clouds move across blue skies and sunlight cross continents as Earth rotates. Then the transmission ends, Outside, Proxima Centauri remains fixed above the horizon. Air made by machines moves through underground rooms. Water recovered thousands of times flows into farms. A locally manufactured valve opens. Children study the systems they will inherit. Humanity has not found another Earth. It has learned how to remain human without one.